This is lecture number 24 of course 7314 Fluid Mechanics 2, and this is the third lecture of this week. We have already addressed the Turbomachine performance, and we will extend the same thing. In the first thing, we will go to this pump system curves, draw the system curve for the pumps, and then we will go into the series in parallel arrangement of pumps. And then we go into the affinity laws or similarity relations, which works for a pump. And in the end, the idea of specific speed for a pump will be addressed. So if you look at the typical arrangement for a pumping system, you have first thing that you have is tank, which is underground tank, and you have an overhead tank. So this is a check valve, and then pump, and this is a gate valve, and then it goes to the overhead tank. So the water levels to raise here is 20 feet, and the piping system is 2-inch pipes of schedule 40 galvanized iron pipes are to be used. You see the check valve is actually, it is a one-way valve like a diode, so it actually allows water to go into the suction side, so the water from the top is not coming back again. So that's why this valve is called a check valve. And gate valve is a normal valve, just open it so that we can take the discharge from the pump. So we know that there are head losses associated with this pumping system, includes some of the head loss in the pipes. So dia of the pipe is D, the length of the pipe is L, and F is the friction factor. So if you use different types of pipes, so that would be contributing to the head loss from Darcy-Weisbach equation, and V is the velocity, and so that head loss would be higher if the length is higher or the diameter is smaller, or if F here is the Darcy friction factor. If we have a higher Darcy friction factor, which is a function of Reynolds number, so you work out that some of the losses in the piping system depending upon the number of pipes involved. And then you have some connectors like valves, like turnings, like gate valves. So all these things contributing to these are called as components. So we can work out the head loss associated with these components, and these K factors are given in different tables. So for example, for this geometry, you have a velocity V, diameter is, and the cross section is this, and your this radius is R. Then you can work out this head loss due to that component if there is a pipe and then there is a reduction takes place. So at different values of R over D, you have different values of this K factor. So, and if you multiply by the K factor with V square over 2G, then that you will be able to calculate the head loss in that particular component, or it could be a gate valve, or it could be in different handbooks and tables. These K factors are given, or sometimes they are called minor loss factors. So this is something a major loss factors which is taking place in the pipes, and these are the taking place in the different components and accessories in the piping systems. They are called as minor loss factors. So after knowledge of this, you will be able to get the expression for head loss, and you know the head loss is head supplied would be actual head gained by the fluid plus the head losses. So as we know that our head losses are head that we need to supply is some function of volume flow rate. So all these V square over AGs to be velocity, by having a knowledge of the area, you can convert it to in terms of a flow rate. And then what you need is to use those performance curves supplied by the particular pump manufacturer, where the volume flow rate is given in the horizontal axis, then the head given in the, or the pressure rise given in the y-axis. and these are the different impeller sizes. So first you need to draw the your system curve, your requirement, let's say that is starting from 20 feet and onwards. As Q is increasing, this is increasing. So you draw the typical by drawing on the system curve onto this performance curves. You will be able to get different operating points. Like for 5M impeller, you will be able to get less than 40 gallons per minute of the flow rate with the head slightly greater than 20 feet. And similarly for 5.5 inch impeller dia, you could have this, let's say if we need an 80 gallon per minute requirement, so it is lying between 6 inch and 6.5 inch. So at 6 inch our volume flow rate would be less than 80, so we need 80, so we must have to look for some 6.5 inch impeller dia. And obviously at the from the previous curve we can see the percentage that is actually corresponding to around 80, and 6 inch dia the percentage is something between 60 and 65. So that would be the efficiency of the corresponding pump. So this is how what we do is we develop those system curves, and we will be able to select which type of impeller at the given speed that is something suitable for meeting this system requirement. Not always we have this single pump to be used. In most of the cases, if your flow rate requirement is higher, what you need to do is you need to use the higher, bigger size pump. So smaller size pump, or sometimes you need an RPM. For example, if we go back to this curve, at this RPM, at this operating RPM of the motor that would run the pump, if it is different, then you have a different performance curve. So I mean, it is just a trade-off between different variables like head, pressurized, volume flow rate, efficiency, and the size of an impeller and the speed of an impeller. So these are all the variables which are important in evaluating the performance of a pump. And in general, the same idea goes with the turbines as well. The only difference between pump and turbine is you are extracting power from the fluid in turbines, and in pump you are supplying power to the fluid. Okay, so there as a possibility of using pumps in combinations. For example, if you're using a single pump, one pump, so you have this typical performance curve. So this is your head, pump head, and this is your volume flow rate. So this is your so-called shut-off head, where volume flow rate is 0. So if you are using two similar pumps that are actually placed in series, so it means the total head for the combined pumps would be higher, which will be a combination of these two heads. So in this way your performance curve would be shifted upward. So and then you have to see how your system curve is going. So this series arrangement is to be used when your system curve is your flow rate is not much changing, but your head requirement is much higher. So you need to lift or you need to increase the pressure head, or you need to lift to more height. Then what you need is to use two pumps in series. So that is what is usually done in the multi-stage pump. So so that your head you don't want much flow rate, but you want more head. So you use the two pumps to be combined with series. So what will happen is the fluid is coming from one pump, and the exit discharge of the first pump would be the inlet section of the second pump, and so on. So in this way we will be able to get higher heads. If you combine in parallel, it means you are not interested in increasing the head. So if your system curve is a much shallow curve, not a steep curve, if it is a steep curve, then the series arrangement is preferable. If it is a less steep curve, so less steep curve means you are not going to increase much head, but you are going to increase more volume flow rate. So for one pump, this would be your for this head, this would be your volume flow rate. For the same head, your volume flow rate is much bigger if you are using the two pumps in parallel. Let's see, not always the pumps are arranged with the similar, two pumps are arranged in series or parallel, but it could be a possibility that let's say the first pump is of bigger size and then the second pump is of a smaller size. So here you have two dissimilar pumps that has been arranged in series, so that this is an inlet of the first section of the first pump, and this is the discharge of the first pump, and this discharge of the first pump going into the section of the second pump. So that is actually the series arrangement, whereas the parallel arrangement is look like, so you have one inlet, and then the fluid goes into this pump as well as into this pump, and this would be your total flow rate. So the flow rate from bigger pump and smaller pump together would give you the higher flow rate. Here you are increasing the pressure so that in the end you have some higher pressures. The problem there, if you are using dissimilar pumps in series or parallel arrangement, we will look at more closely into the performance curve, that what the problems are. So, but usually whenever you have to use, in order to avoid the problems, these problems becomes more significant if the sizes of the two pumps are significantly different. If they are nearly the same, then the combinations won't have some problems like backflow, some problems like loss of the flow rate, or some problems like loss of the pressure rise. So all these problems we will address in the coming slides. Okay, now look at more closely the performance curve of the two pumps which are in series. So let's say this is a pump A, which can give me some head HA, and we have some pump B, their head is somewhat smaller than the head for A. So it means these two pumps are actually the dissimilar pumps. So when we combine these performance curves, so this would be the combined performance curve of when you have combined them in series, and then obviously you have to match with your system curve so that you can get your required points. So for this combined flow rate, this would be the head you are going to get which you needed, and your pump is quite capable to supply that head. So this is your system requirement, and this is your pump that head that pump can provide. So that would be one of an operating points. So if obviously, as you know, that the behavior of the combined pump is actually depending upon the performance curve of each individual pump, because the performance parameters like pressure rise or head or volume flow rate are different in pump A and B. So if you look at pump B or pump A alone can give you some higher flow rate, whereas pump B can give you, for example, if your head is this requirement, so your pump A is giving you more volume flow rate than pump B. But if you combine them together, so your at that head requirement, your volume flow rate for a combined would be much lesser. But for the same volume flow rate, if you go to combined head, your head has increased. So this actually brings us the issues when you combine two dissimilar types of pumps. So normally your head is actually when you put in series, so your generally you need a higher head. So but if you have two pumps which are working separately, if you add their head, your combined head would be slightly less than that. So it is and at a given flow rate, actually if your flow rate is at a fixed. So series arrangements are useful when you need to increase the head, but what you need is your flow rate must be same. So then the series arrangement works fine. If you look the parallel arrangement, so in that parallel arrangement you have a pump A, which is giving you more head and more flow rate. So obviously it would be a bigger size pump, because on performance curve that impeller dia would be higher than this, and this pump B is a smaller pump. So if you put them together in a parallel network, then what you are going to get is more flow rate. So the total flow rate for your combined pump which are in parallel would be obviously greater than the flow rate of pump A or B either, because that number must be greater than that. So your flow rate for combined would be obviously greater than the their individual flow rate would be bigger than this combined flow rate, but we know that the flow rate of A and B together would always be greater than A. So because this is a smaller flow rate, and obviously it all depends on what head you have. For example, you see here the pump A is having a bigger head than pump B. But what we have to do is once we are combining it in parallel, so the maximum head you get is not for the higher head of pump A, but you will get the combined head would be the head of the pump B, which is lower value than A. So the in parallel arrangements, actually the intention is to increase the flow rate. So but your head would be goes to the lowest head that is available in A and B. So that would be in this case it is the head of the B. So combined head would be here, somewhat here, would always be less than, would always be the same as cannot be more than the head of the smallest pump. So so it is if you have different sizes of the pump arranged in parallel, so the shut-off head, this is your shut-off head. Shut-off head means the head when your flow rate is 0. So that would be not more than the shut-off head of the pump B. So that is actually the limitation when you are combining pumps in parallel. If you see more closely the performance curves, let's say here you have not one pump but 3 different pumps. So pump 1 is a smaller pump, pump 2 is much bigger pump, and pump 3 is that pump. So once you are combining them in series, so if you see at this flow rate, for example this flow rate, pump 1 only gives you this head, pump 2 gives you this head, pump 3 gives you this head, but the all 3 pump in series would give you the some bigger head, which is actually a combination of the head of 1, 2 and 3. But this situation is not the same once you go into some higher flow rates. For example, here your flow rate is actually this flow rate is actually you have a maximum flow rate which is coming from pump 1. So it means pump 1 is cannot give you any flow rate if your flow rate requirement is higher than this. So this is actually called the free delivery of the pump 1. Free delivery of the pump 1 is the maximum volume flow rate. Obviously your head, there is no head available. So the head is 0, so that would be your free delivery or free volume flow rate. That volume flow rate when your head is 0. So if you see here, apart from this line, red line, so your requirement, your pump 1 is something should be shut off or should be bypassed, because now what you are going to get the head for this flow rate, your head is actually coming from pump 2 and pump 3 only. And after this volume flow rate, the combined would be only from the pump 3, because pump 2 has already dropped its flow rate to 0. So in this case, pump 1 and 2 must be bypassed or shut off so that you get the flow rate. So the performances are different at different operating conditions. So if your volume flow rate is low, let's say here, so head is supplied by all 3 pumps. When you increase your flow rate, then only 2 pumps can supply the head, because the pump 1 already has exhausted, and here the pump 2 has exhausted, so only pump 3 can provide you the head. But obviously the operating conditions are not set as so that you could have a very high flow rate. But so the arrangement is work only, for example, with low volume flow rate, all 3 pumps can provide you the head. So if your job is to, application is to increase the head, so you have to keep your volume flow rate should be low, because if you will increase the volume flow rate, might be you need to, that the pump 1 or pump 2 might be ineffective. So this is what I have written here, and you will be able to read it. And the same thing if we look at in this, when your 3 pumps are arranged in parallel. So in parallel, what you need is your head is not that requirement. So your combined volume flow rate. So at low, so it would be opposite at low flow rate, at low head rather, because head is representing. So if your head requirement is low, then you could get volume flow rate from each of those pumps, Q1, Q2 and Q3. And once you are here, so you are only getting volume flow rate from 2 and 3, and once your head is that high, that you can only get volume flow rate from the 3rd pump. So because this would be the combined curve. So this combined curve, just like pumps in series, pump in parallel, also not all are supplying, because if your head requirement is low, then these arrangement for parallel, all 3 pumps would be contributing in the volume flow rate. So the same thing is, but if your all pumps are identical, then you won't have that problem, because this problem comes because once you have dissimilar pump, because pump 1, 2, 3 all are different performance curves. So because the performance curve is related, the head or the pressure rise and the volume flow rate are very much linked through their performance curve. So once you combine them, the combined performance is also affected by these variables. Okay, so I mean, in practical applications, sometimes you have to use combined pumps, just like as you have a one main pump, what you call it a duty pump, or if in case of a failure, you need have some assisted pump or some smaller version of that pump. And sometimes in order to meet the minimum requirement, you need some standby pumps. So there are different combinations that could be required depending upon different applications. For example, once you increase the head, so this multi-stage arrangement is work. For example, all this shaft of all the impellers of different pumps, there are 3 pumps in series, so all are connected with the same impeller and same shaft and with the same motor. So but here the job is not to increase the flow rate, but to increase the head. So the flow rate would be restricted with this speed of the shaft, that would be an RPM of the shaft. And we will see in the similarity and performance curves how these different parameters are interrelated with each other. So such arrangement is called such pumps are called multi-stage pumps. So most of the overhead pumps, you can see they have different stages. The first stage, you increase from P1 to P2 pressure, then P2 to P3, and then P3 to 4, and so on, so on. So if some heat is generated, then you need to use intercoolers so that the temperature of the fluid goes down. But usually that happens in the reciprocating type compressors when you do the multi-staging. So in centrifugal type, actually you don't have much flow rates, but you have some higher pressurized or higher head. Okay, the performances can be expressed in terms of the laws. For example, one of the thing is you need to supply some power to the shaft. There is an RPM associated, there is a dia of an impeller, there would be a density of the fluid, there would be a viscosity of the fluid, and there would be a volume flow rate coming first into the suction side and then into the discharge side. So these are the parameters that are linked together, and the laws which are actually called as similarity laws based on that dimensional analysis. And we learned that once you fix your impeller dia, so your geometry is fixed. Once you keep your geometry constant, so then more the power, more the RPM, more will be the volume flow rate. So it would be directly proportional, and head that was be developed by that pump would be directly proportional to the square of the speed. Speed is the RPM here, revolutions per minute. And the power requirement to run this pump would be cube of the RPM. So here we are keeping the impeller, one impeller, but working with different speeds. So if you change the speed for a given impeller, your flow rate, your head, and your power requirement changes. Similarly, if you keep the speed constant and change different dia of impeller, so in this case, from experiment we learned that the volume flow rate would be directly proportional to the cube of the diameter. So if diameter is doubled, then the volume flow rate would be 8 times. If it is increased by twice a factor, then 2 to the power 3 would be 8. Then the volume flow rate is going to change by a factor of 8. So there is a non-linear relation. Similarly, head would be some directly proportional to the square of the dia, and power requirement would be the fifth power of the diameter. So if you combine these proportionality relations, you end up with such relations like if Q is directly proportional to N, Q is directly proportional to D, and then both are directly proportional. But here it is power 1 and here it is power 3. So you get the relationship between two operating conditions 1 and 2. N1 would be 1 RPM, N2 would be another RPM, D1 would be 1 impeller dia, D2 would be another impeller dia. So you can work out the corresponding volume flow rate. Similarly, you can have an expression for head which is N square and D square, N square and D square. So you can easily work out the expression that would be directly proportional for power would be directly proportional to N cube and fifth power of the diameter. But here as you know, power is rho G H Q. So we will learn that these are related. So in power formula you need the component of the density. So if density is same, then that would cancel out, otherwise you need, so this is the ratio of the power requirement to different operating conditions. So if you see for example this problem, you have a centrifugal pump of RPM 1200, the volume flow rate is given and head is given. So here the shut-off head is 30 meter. Shut-off head means when your volume flow rate is 0. So the question is for what speed the discharge or the volume flow rate will be this volume flow rate, or what will be the corresponding head or what speed will be the shut off head would be 22 meter. So first what is given here is, because this is the problem in which you have fixed impeller, so your dia is fixed, then it means D1 is same as D2. So Q1 is already given, which is 0.5 meter cube per second, RPM is given 1200 RPM, and the head that your pump can supply with diameter D1 would be 20 meters. So what you need to work out, you need to work out the speed and the head when your discharge changes from 0.5 to 0.6. So using those similarity relations, I can work out the speed, I can work out the head. So this is something we have done the first part, and in the second part we have some additional information of the shut off head is given. So we need for that new operating condition N2 and H2, what will be the shut off head, that is something we have to work out. So I call that to be my RPM would be 1200 in the first case, and my volume flow rate would be 0 because my shut off head would be 30. So that is something given here. So it means the volume flow rate when your shut off head is 30, it means your volume flow rate would be 0. So corresponding speed would be N2, and corresponding head at that shut off condition would be, in this way would be, you have to work out the speed when your head is 22 meter. So for what speed will the shut off head would be 22 meter. So using the expression for fixed diameter, because diameter is same in that case, you can easily work out the speed when your shut off head goes to 22 meter. So if one of the unknown is to be worked out, you can easily use those affinity laws or similarity relations to work out. Okay, so these performance parameters we can work out in the dimensionless form. For example, volume flow rate is Q, N is an RPM, D is the diameter. So I can have a dimensionless form of this coefficient. I call it a flow rate coefficient. CQ is actually the discharge coefficient or a flow rate coefficient, which would be Q over N D cube, and then the head coefficient would be GH over N squared, D squared. G is accretion due to gravity, H is the head of the pump, head rise by the pump, N is the RPM, D is the diameter. Similarly, we can have this power coefficient. So power requirement is this. When a power requirement, then rho is there, speed is there. So these are the dimensionless coefficient, just like the numbers which are involved in working out the performance of a machine. Just like the same as you have dimensionless numbers like Reynolds number, which takes care of the density, velocity, diameter, and viscosity. So here we have in turbo machines or in fluid machines, you have such dimensionless number, and we can easily work out its relate it with efficiency. Efficiency is if you substitute all these parameters, if you substitute CQ, if you substitute CH and CP, and multiplied with the head and the flow rate coefficient divided by the power coefficient, you are going to get the efficiency of the pump. And similarly, you can work out the efficiency of the turbine if your CP is in the numerator and CQ and CH in the denominator. That we will work out when we will talk about turbines. So if you just substitute here, you will end up with that is actually the power which is gained by the fluid, so that its volume flow rate is Q and head is H, and the power requirement, which is T times omega, then this would be P. So that relates these dimensionless numbers relates with the efficiency. And sometimes we plot it in the form of the graphs, like CH is plotted on this axis, CP and efficiency is plotted on this axis, and CQ is plotted on this axis. So what I see is as CQ increases, your efficiency also increases. So at some flow coefficient, it is a maximum efficiency, and your head coefficient is some constant value, and then it's constant and then start decreasing. And similarly, the power coefficient work in that manner. So that is something for a radial flow machine, that is actually a centrifugal pump. And you have similar performance curves for axial flow machines. So your axial, so what you see from these two curves is centrifugal pumps are good, having higher head coefficient. It means you are supposed to get more head in your as far as your centrifugal pumps are concerned. Whereas axial flow pump, your heads are much lower. Even though the scale is not same for these two curves, but if the scales are same, then you can easily compare them. So these are actually called as dimensionless performance curves. So different machines have different performance curves. I mean, based on that, we invent one more parameter, which is actually called as pump specific speed, which is nothing. We are using the flow rate coefficient or discharge coefficient and head coefficient, and flow rate coefficient with power half and head coefficient with power 3/4. So these powers are very interestingly taken. I will tell you how actually people have done. CQ is this flow coefficient, and CH is, and if you simplify, so what you end up with, very interestingly, you end up with, because here power d to the power 3/2, and here 2 multiplied by 3/4, d to the power 3/2. So d and d cancel out. So it means this parameter is interestingly is independent of the size of an impeller. So only you have an operating condition like flow rate, RPM and head is given. So you can work out that number, that is actually called as pump specific speed. And we can do it in different forms, like we can, instead of flow rate, we can convert it into power requirement. Then this formula for a specific speed would be n times under root power, that is in kilowatts, and the head. So these are another because they are taking care of the dimensionless coefficients. So you end up with another dimensionless numbers, but these dimensionless numbers are useful in classifying different types of turbo machine. For example, centrifugal machines, which are flow is something like that. The blade shape is such that flow comes in from an eye of an impeller and then moves in the radial direction. So they are radial machines. So where specific speed in this unit is order of from 0.2 to 1. So, and your efficiency is plotted for centrifugal machines. So which is, for example, that specific speed efficiency is much higher. So if you know the specific speed, you can say less than 1.5. If your specific speed for pumps, your machine would be centrifugal type machine. Or if it is between 1.5 to something like 3.5, then you have a mixed flow machine. Or if your greater than specific speed is greater than 3.5, then you have axial flow machines. And you see, compared with centrifugal, mixed and axial flow machines are not the strong functions of the specific speed as far as their efficiency is concerned. So nearly they have 90% efficiency. So if you know the specific speed, you can classify the turbo machine, because each class with obviously at a given efficiency, each class of each number is signifying a particular class of turbo machine. So this specificity concept is very useful in classifying different turbo machines. Okay, there is a problem related to this turbine specific speed. You have two homologous pumps. We will see what homologous means. A and B to run at the same speed of 600 RPM. Pump A has an impeller of 50 and a volume flow rate of 0.4 of water under a net head of 50 meters. So head is 50 and Q is 0.4 meters and RPM is this. So what you need to determine the impeller size of the pump B, if its net head and its net head to be worked out, if its discharge changes from 0.4 to 0.3 meter cube. So your pump B has some lower discharge. So once we say two pumps are homologous, it means they are belongs to the same category. So I have missed the symbol here. Actually, I use the symbol actually for specific speed is NSP. It's SP. SP, I must write it here. So specific speed for two pump, if they are same, it means they belong to have the same specific speed. So specific speed for pump A should be the same as specific speed for pump B. Okay, so that is what is I have written here. That's it correct here. Actually, that is some, this information is given because they are running at the same speed. So I'm sorry, this is actually the same speed. So pump A and pump B are both running at the same speed. And when you say homologous, it means your specific speed for pump A is same as the specific speed for pump B. So I have the formula for specific speed for pump which is RPM times square root of the flow rate and head. So I got the specific speed of the pump A. So here I just know the speed of the pump B and the volume flow rate of the pump B. I can easily work out the head of the pump B because two pumps are homologous. It means their specific speed are identical. So I have worked out the head for the pump B. Second thing that I have to work out the impeller dia. So as I know from affinity laws, I can easily work out the diameter of the pump B. So in this way we can solve problems because two pumps are homologous. It means their specific speed is identical. So in this way we can work out the unknowns, which so such set of problems can be easily solved using combining the concept of specific speed and the affinity laws. So at this point I stop the lecture.